Ahora sí. Excuse me. Dr. Tokunaga made his PhD in astronomy in 1976 at the State University of New York at Stony Brook on high-resolution spectroscopy of Jupiter and Saturn at 10 microns. Since then, he's been a postdoc in NASA Ames in 1976 and 1977, a research associate at the Stewart Observatory until 1979. Since then, he's been working at the Institute for Astrophysics in Hawaii, first as an assistant astronomer, as an associate astronomer. He was the associate director for research support and the Institute from 1990 to 1992. And since then, since April 2000, he has been the IRTF division chief. Dr. Tokunaga has more than 100 papers published in planetary science, star formation, interstellar medium, and astronomical instrumentation. In particular, he's been an instrument reviewer of several instruments that are already installed on Gemini, Subaru, Keck, and also for Rosetta mission. So I will invite Dr. Tokunaga to start his colloquium.
Okay, thank you. This is a little bit unusual talk. It's about small telescopes and large telescopes. Small being 3 to 4 meter class telescopes. And this talk has about 3 separate topics. The first one I'll talk about is flexible observing. Actually, it should be flexible remote observing at the IRTF. And since we're a small telescope, 3 meter class, we've tried to address the needs of the community more closely than larger telescopes. And we've gone to flexible remote observing. I'll describe in detail what we do. I think you might find it interesting. Second topic is a short discussion about an immersion grading spectrograph that we are planning to build for the IRTF. Since there is instrumentation here, I thought this would be a suitable topic. But it also shows what we can do with a 3 meter class telescope that is unique. The third topic is about the growth of telescope aperture. And I have a simple question: is there a limit to how big we can make telescopes? And tie that to the role of small telescopes in the era of large telescopes. So that's the basic outline. First, I wanted to show some similarities I noticed in looking at my guidebook. So Mauna Kea, as some of you may know, means white mountain in the Hawaiian language. And Tenerife, according to my guidebook, also means white mountain. That's interesting. And Hawaii and the Canary Islands have active volcanoes. These pictures from volcanoes in Hawaii are very recent, in the last 2 years. Another interesting similarity is that our institute at the University of Hawaii has facilities on 2 other islands, much like the IAC. The main headquarters building is in Honolulu, on the island of Oahu. But we have a solar observatory on Haleakala, and also the Pan-STARRS survey telescope is here. And on the island of Hawaii, we have the Mauna Kea observatories. And just a brief short description of the summit of Mauna Kea. So the IRTF is here. It's getting hard to notice with all the large telescopes nearby. And if you stand in the right place, the dome looks very impressive compared to Gemini and SAVE-HD. Yes. So I'll talk a little bit about the IRTF, since some of you may not be familiar with it. It's operated by the University of Hawaii under a cooperative agreement. It's like a contract with NASA. And operations started in 1979. And the primary purpose then and now is to provide mission support. And all of the funding comes from the planetary astronomy program within NASA. We get no money from the astrophysics side. So our primary focus is on planetary astronomy. And when I talk about flexible remote observing, I'll explain how we use flexible remote observing to support planetary astronomy. And we are currently supported under the current cooperative agreement to 2013. But we're building a new instrument, or at least I hope we'll be building a new instrument and extend the life of the telescope well beyond 2013. This shows a picture of the focal plane of the telescope. And one thing to notice is that we have our instruments mounted on the back end. We can keep up to 4 instruments mounted and ready for use. Our primary reason for doing this was that we found that there were many problems in changing instruments. And so we got the idea of, well, let's keep the instruments on the telescope all the time, avoid instrument changes, and there'll be less downtime. This, in fact, turned out to be correct. I mean, that it worked out in practice. So what we do is we have 4 positions. We can switch one instrument into the center position. And this became very useful when we implemented remote observing, because we can switch the instrument during the night.
How long does it take?
It takes about 20 minutes to do a switch. So it's a little bit different from the U-Kurt, where there's a rotating dichroic, and the switch can be done in a few minutes. But the reason we chose to do it this way is we wanted to keep our instruments up-looking to avoid the dichroic. And this shows the picture of our main facility instruments. So Seashell is a high-resolution spectrograph. The maximum resolving power is 40,000. It's a very old instrument. It's over 10 years old, and I'd like to replace it with the immersion grating spectrograph, which I'll describe shortly. SPECS is a moderate resolution spectrometer. Maximum resolving power is about 2,500. And it has a very popular prism mode with about resolving power of about 150 to 200. NSF-CAM is a 1 to 5 micron camera. And then we also have a 8 to 25 micron camera. And you can sort of see how this, right now, SPECS is in the central position, and we can switch it out, put another instrument in during the night. We also have what we call community-based instruments. These are primarily 10 micron instruments. The most interesting one is TechSees, which has a resolving power of 100,000. And we currently share it between IRITEF and Gemini. We switch every semester. We have a heterodyne spectrometer, which provides up to 1 million resolving power, and a low-resolution spectrograph that covers, it's actually 5 rather than 3, 5 to 14 microns in one exposure. These instruments are made available to visitors, so anyone can apply to use these instruments, although they're supported by the PIs. We don't support these instruments. And unlike larger telescopes, we actually welcome visitors to bring their instruments. Okay, now I'm going to talk about remote observing. Here's a picture of Rick Binzel. He's in the remote observing room at MIT. And from this picture, I can't actually tell if he likes or doesn't like remote observing. But I think he actually likes remote observing. He doesn't come out anymore since we offered remote observing. And this is a typical setup. So there's this set of graphical user interface for the instrument is exactly what you would see if you went to the telescope. There's no difference. And I'll show a demonstration of this later. And he bought a Polycom camera to support his remote observing. And so I'll discuss this more later, but one advantage of doing remote observing like this is that he can involve many more students than he normally would be able to do if he had to fly out every time. So here's a lot of words here, but basically the pros and cons of doing remote observing or staying at home or going to the observatory. Some of the main differences are that if you go to the observatory, you have more control over the observing. It's also good to be at the telescope when you're using it for the first time. From remote observing, it's hard to get a feeling for what's actually happening on the other end unless you've been there at least once. So we do recommend people to come out at least one time, preferably the first observing run, to learn how things work. More important things are that, to me, it seems going to the observatory is necessary for training students. There's the excitement of actually being at the observatory. You can look at the sky, and you can focus completely on the observing. There are senior observers who come out specifically to get away from the office. The remote observing has advantages, however. It can allow for very short observing slots, time slots, like even as short as 1 hour. I'll show some examples later. And you can have as many participants as you want on the remote end. And it's compared to being at Mauna Kea, it's much better to work at sea level. Okay, here's this plot shows the increase in remote observing over the years. We started in 2002. It's gradually increased, so now you see that it's between 50 to 60% remote observing. And this is under a method or a system where the observer can choose. We don't impose any condition for observing. If people want to come out, they are free to do so. If they'd rather stay at home, they can do so. It's probably not going to be much more than 50 to 60%, is my guess. However, if the airfares keep increasing, this could go to 80%, I think, at some time in the future. There's no restriction on the location. You can observe from your office, the home institution, from Hilo, or from our mid-level facilities where the dormitories are, called Halepohaku. We've also had observers from Europe, Paris, London, and also we have one observer from Brazil and one observer from Puerto Rico. So it's really virtually unlimited in terms of accessibility, even from your home if you have the proper bandwidth. Time slots as short as 30 minutes are possible for remote observing. And instrument changes are possible during the night so that we can have multiple programs during the night. So it provides considerable flexibility in the scheduling. But as you'll see, this complexity is difficult for the scheduler, which is myself. So here's becoming a typical schedule now for the IRTF. It might be hard to see in the back of the room, but this is 1 month, and each column is 1 day. So right here, this is a block of 3 nights using, this is program number 006, observer is Harderson, instrument is SPEX, and the time slot is 1800 to 6 o'clock a.m. Okay. And there's also examples, here's an example of 3 observing programs in 1 night. I'll show a block later. Red means it's remote observing black means classical observing. So the black bars means someone came out to observe. Okay, I show the next slide here. Okay, this slide shows a blow-up of the previous one. So here you can see in this one night we had 3 different programs. This symbol here means it's time critical. So this was a program observing a particular near-Earth object and required a particular time slot on this day. So this is a program I can't move. So when I schedule it, I put it down and then I schedule around it. And it just so happens there are 2 other programs that can use time before and after this time slot. So I schedule them into those time slots. And since it's remote observing, people don't come out, it's quite feasible to do this, no matter how far away they are. Here's an example where on one night we did an instrument change. So this person, Kobuna, was observing Venus with the high resolution spectrograph. Then we switched to a second program, Bojorkman, using specs, and this person was observing stars. Is that me? Or what? Can I do something about that? Okay. Let's see if I maybe if I stand behind the speaker. Okay, no, it doesn't help. What was I going to say here? Okay, in this slide, I'm showing a somewhat even more complex situation. So in addition to the highly fragmented schedule, we've added a service observing program, which is shown in blue. So this particular service observing program lasts for only 20 minutes. It's to observe Titan. The requirement is to observe Titan whenever this instrument specs is scheduled. And the observations are done by executing macros by the TO. So the TO will slew to Titan, and run the macros, and that's the end of the observing. The data is on the disk, and the investigator will pick it up later. This type of scheduling is what I think is needed for planetary astronomy. I'm not suggesting that every observatory attempt this. This is very difficult to schedule. But for planetary astronomy, there are many situations where someone wants to observe a particular asteroid that's flying by the Earth, and it's only a very short time slot. We also have time variability observations. We have one program to observe Triton, satellite of Neptune, for 2 hours once a month throughout the year. And we can accommodate that. We also have cases of an occultation of the satellite Io around Jupiter. These occultations take maybe half an hour. We can schedule a half-hour time slot for that. There's also another interesting program that we are accommodating. If I go back a little bit. Oops. The program by Jim Elliott, MIT. This is one. Here he is, and here he is again, and here he is again. This particular program is to observe occultations of a planetary system or a star by an exoplanet. So these time slots are very critical, cannot be moved. They're for very specific dates and times, and we can schedule that. And we schedule it only for the amount of time required. And this shows how I used to schedule the telescope. It was very easy. People would fly out to observe the instrument, to observe at the telescope. So it was not practical to have observing slots. Okay. this kind of flexible remote observing I found to be quite interesting once we implemented it. There were things I had not thought about that people started using remote observing to suit their needs. One interesting thing is that you can have remote observing from multiple sites at the same time. Okay? So very typical case is one observer observing from Boulder, Colorado, and his or her collaborator being observing in Flagstaff, Arizona. They will both log into the system and see exactly the same thing on the computer display. Of course, only one person can actually do the observing. They have to decide beforehand who's going to be driving the telescope. But they can both participate in the observing together, even though they're separated by a very large distance. I also personally had a situation where I was observing in Honolulu. I had a collaborator in Pasadena, California, and another collaborator in Erie, Pennsylvania. And we all observed together looking at the same computer screen. I controlled the instrument, and the person in Pasadena did the data reduction as we were taking data the night. Another thing that I mentioned is that new kinds of observations can be proposed. You can propose to observe 1 hour per month for 6 months on a particular target, if that's what you need. And we can accommodate that. We can have multiple short observations. For such observations like 1 hour, we find that people quite often observe at home. There's more student access at the home institution. In the case of MIT, the professor there, Rick Binzel, has a lot of students doing remote observing for him for training, but he sends only the best students out to Mauna Kea at least once to give them a feeling for what the observatory is like. No, they volunteered. And the target for opportunity can be handled by remote observing. So we have a supernova program. Occasionally they will call and say, well, we need to observe the supernova tonight or tomorrow night. I'll call the observer who's scheduled. If that's okay, then we have the target of opportunity observer log in for 1 hour to do the supernova. This is what the observer sees. This shows us one screen. This particular instrument is SPECS, and it requires two windows. It shows one of the 2 windows. So the remote observer sees, as I mentioned earlier, exactly what he or she would see if he went to the telescope. And we have a little window here. This is iChat using Macintosh software. But one can use Polycom or Skype. But we find that it's not necessary to have visual contact. The minimum would be a phone line. And that works quite well. And we have a telescope information here, position and offset information. And we also have a software hand paddle. So this portion of the window can be used to center up on the object, just like being at the telescope. The method that we use for supporting remote observing is software called Virtual Network Computing, VNC. It's very flexible, can handle any platform. So we have our instrument here and a VNC server at the telescope. So these 2 items are at the telescope. Then through the internet, we have a remote observer using a VNC client software. And it's platform independent. So whatever platform you have, you can download the appropriate VNC software to run it. And then the remote observer can control the instrument just like being at the telescope. Okay, and then we have a live demonstration, so we'll see how this works. Hi, Paul. Can you hear me?
Yes, Doctor.
Okay. Okay, this is Paul Sears. He's our telescope operator at the IRTF. This is live, so we can actually ask him questions. What's the observer doing, Paul?
We're looking at a star. Just about 4.5 minutes left on this observation.
Okay.
Guiding away with guide dog and doing a spectrum with big dog.
Okay, good. It's 12 midnight there in Hawaii right now. And can we have the other?
What type of stars are you looking at, Caitlin?
This is a candidate brown dwarf.
All right.
I should say now it is a confirmed brown dwarf.
Oh, congratulations. What's the magnitude?
What's the magnitude, Caitlin?
This is a J of 16.6.
Okay, 13.6 J magnitude. Okay, now this screen is showing what the observer is seeing right now, okay? And I'm showing this through VNC. So you can see the integration is proceeding and the time left for the integration is decreasing. This is specs. Yeah, it's being used in a prism mode. So this is the spectrum in a prism mode. Yeah. And this shows the second screen, image of the slit. And this is the auto guider. So what it's doing is it's looking at the, this is the center of the slit and where the cross is. And it's going to move the any light that is spilled over. It uses that to provide auto guiding. So it'll try to minimize the amount of light that is seen on the slit. How's the weather, Paul?
Very nice. It's clear. 4% humidity. It's rather warm. We're 6 degrees Celsius outside.
Okay. The
seeing's 0.45.
The seeing is 0.45?
Yes.
Oh, excellent. Okay.
Yes.
Is it, that's an infrared. What, is it a K? Is it a K?
Yes, that's in the K filter.
Okay. Yeah. So it's not as good as it seems. Okay. So one disadvantage is you can't really see the sky, but we have sky cameras that allow some information, and you can also ask the telescope operator to go outside and sky. Okay, I think that's enough probably. Okay, thanks, Paul.
You're very welcome.
Okay. All right, well, that was fantastic. It worked. We do worry about security. So at the moment, all external ports are blocked by a firewall except for the ones that are used by the VNC server. The password is changed daily. This is partly for security, partly to avoid two people trying to use it at the same time. And we set up the instrument so that they have a permanent VNC session numbers. And that makes it easy for the support people and for the observers. And one use is that they don't care. This method of using in the observatory is very useful for supporting instruments, especially troubleshooting. Okay, now if you remember how complex the schedule is right now, you might not do queue scheduling. So queue scheduling, by definition, would be that the observatory staff takes all the data, and we just ship the data to the principal investigator. The pros and cons of queue observing have been debated quite a bit. This is a good reference I found on in the early days before Gemini was commissioned. Discussions regarding is queue scheduling useful or not, and do people want queue scheduling? It certainly is useful. I mean, if you have to have 0.3 arcsecond seeing for your observation, queue scheduling allows, in principle, the ability to wait for that very special seeing conditions and then provide the data for you. We have not considered queue scheduling. The main reason is we don't have enough euros, or in our case, dollars. And I would prefer, I wish I could change the dollar sign to a euro sign and go to the bank and convert the money, convert it to operating funds. But we don't have enough dollars to do this. It requires quite a bit of overhead for the observatory. Second reason is that there's no apparent demand for it. I haven't had people come to me and say, well, we have to have remote queue observing. I think the reason is that remote and classical observing, as we practice it, permits changes as the observing proceeds in real time. It allows the observer to see exactly how the data was taken and allows engagement in this process of doing the observing, which is important. There's also a very good discussion of by Lockman on these issues of service observing versus classical observing. The title he used is, "Can remote observing be good observing?" He really meant, can queue observing be really good observing? He's a radio astronomer, and nearly all the data taken by radio astronomers are done in queue mode. So he had thought about this carefully, and it's a very good article. In our case, there's another consideration, which is time-critical planetary observations are subject to the weather. So, since we're primarily concerned with planetary observations, there's no inherent advantage to doing queue observing. And also, many of the planetary observations are a little bit more complex, and it's hard to specify every detail for the planetary observation. I've asked myself the question, are we at the limit of what we can handle as we are practicing remote observing? My feeling is that we're pretty make the schedule any more complex than it is already. But there are some possibilities for more productivity. This includes scheduling backup programs. So a 10-micron program could have a backup near-infrared program. There could be a backup program for times of bad seeing. There can be also, one can also consider what the UCURT calls reactive scheduling, that is, allow additional remote observing to complete high priority programs. Sometimes you need 10% to complete the project, and it's possible to consider setting aside some time to allow completion of projects, specifically for completion of projects. We could also consider a mixture of queue and remote observing, but it's not likely because of the increased cost. Whatever we do, the values that we'd like to preserve would be flexible scheduling, which is required for planetary work, easy remote access, as you just saw, and the observer controls the observations. Oh, yeah, why is Q observing more expensive? Well, you have to hire an observer 365 nights a year. The observer has to be competent enough to take data at least as well as a good observer. The data has to be archived, and there's all kinds of management regarding the archiving process and delivery of the data to the person. And I think as practiced by Gemini, they will also reduce the data for you. So they're trying to make it like as close as possible to taking care of most of the thinking regarding getting the data, and let the observer just worry about the analysis. One measure of this is that the Gemini operations are running roughly 20% of the capital cost, and I think roughly. And the typical number is 10% for a normal observatory. So their operating cost is high, partly because of the Q scheduling. 20% per year. Okay, I'll change subject here, unless there's more questions about the first part of the talk. Okay. Yes, our staff does not do any observing for observers. So you don't have astronomers? We have 3 support astronomers. If you include myself, we have 4 astronomers on our staff. Okay. I'll have to run through this quickly because I'm running out of time. And I'd like to save some time for the last subject, which is large telescopes. I think there's some very interesting questions about large telescopes. I've submitted a proposal to the National Science Foundation in the U.S. to build an immersion grading spectrograph for the IRTF. This is a high-resolution spectrograph, and these are the co-investigators. These are the rough specifications, slit width of 0.25 to 1 arc second. 0.25 arc seconds is chosen because we're emphasizing the putting priority on the 3-micron window, where there are a lot of molecular bands. And 0.25 arc seconds is the diffraction limit of the IRTF at 3 microns. We'll achieve roughly 70,000 resolving power at 3.5 microns. Let's see, and we're using a 2K by 2K, a Mercad-Telluride array. This shows a simple layout of the instrument. Like specs, we're planning to have a slit viewer, which is this portion of the instrument. And the rest of the instrument is very standard, except it has an immersion grading. Okay, now just a very quick few words about the immersion gratings. The top figure shows a grating in reflection. The light comes in from the right, is diffracted by the grating. So this is pretty. This is what you would typically think of for grating. In the case of an immersion grating, the light enters a dielectric material. The material that we are using is silicon, with an index of refraction of 3.4. In a dielectric material, the wavelength shrinks in proportion to the refractive index. So it's like in the material, the wavelength is 3 times smaller. So the optical path difference is 3 times larger. And this is what gives the greater dispersion in immersion. And this gives the paper describing the process of producing an immersion grating. There are different ways of doing it. They're doing it in one particular way, which is by etching the silicon. And you can't read the words, but don't worry about it. The material is cut. A mask is put on the cut surface. Then it's illuminated by UV light. Then the parts of the mask portion of the silicon that's not masked can then be etched away in a solution. So after the etching process, you have grooves, and the angle of the grooves is controlled by how you cut the silicon. And this shows a finished product here. So I don't have too much time, so just go very quickly. This shows a photograph of an actual immersion grating that was produced by the group and by this group at the University of Texas. The PI is Dan Jaffe. And I've been collaborating with him, so he's reserving this particular grating for our instrument. So provided we get funding from the National Science Foundation, we can use this grating in our instrument. So getting the grating is the hard part. It would be impractical to propose to build a spectrograph of this type without having the grating in hand. And this shows a electron microscope picture of the cross-section of the grooves. So it's very nice, but there are many technical difficulties in doing this. It took them about over 10 years to develop the processing techniques. The other way you can make gratings like this is to use a diamond turning machine, but that has other problems. And this shows a spectrum taken with that grating in immersion at a wavelength of 1.5 microns. And so the performance looks very good. What we're looking for would be any signs of ghost lines. We don't see any. Okay, so that's the immersion grating part. So I went through that very quickly, but we can talk about it later if any of you have questions. So I wanted to end this talk with a few comments about large telescopes and tie that to small telescopes. I got thinking about large telescopes in the way that I'm presenting it when I wrote a review article for an encyclopedia on telescopes. And got me thinking about certain things. This is an interesting plot from a paper by Racine. You can see that, well, let me define some of the symbols here. So the black solid dots are reflectors. So this line is showing like the upper envelope of the largest reflectors made over time. Now he's thrown out larger reflectors that were made, but were scientifically useless. So these are shown by the crosses. Okay? So he doesn't draw any conclusions from those points. And then the diamonds are the planned extremely large telescopes. Okay? So they're up here. And they're above this line. So what's interesting about this is that you can see that over a period of about 300 years, the upper limit of telescope aperture roughly follows this line. And then we come to the present day, and then we see the projected increase in telescope aperture. And the question is, well, okay, what's happening? Why is this possible? Okay, and what are we doing differently that allows things to change so dramatically? Of course, they're just proposed projects. They haven't been built yet. So, there is a question of, is the limit going to be here or here or here? We don't know yet. Okay, this is my own plot. Let me go back one here, just to be sure there's no confusion. This is diameter, okay? And here I'm plotting area. Okay? I like plotting the area because it seems to me the cost is going to be somehow a function of the area, and it seems easier for me to visualize that. But the same kind of same data that Racine has. And here I've drawn a line since the year 1900, and it's a surprisingly good fit for astronomical papers. It's actually a very nice fit. And here you see the extremely large telescopes. I've plotted them in the year 2020. And here's a GTC, by the way. I plotted it at 2008, and slightly larger than the Keck, as you can see. The LBT is a large binocular telescope. That has 2 8-meter telescopes on a single mount. Okay, now here's a blow-up of that last part of the plot. Okay, you see the doubling time is about 20 years. Okay, then something's happening here, and the question is, well, what's happening here? It is conceivable that the doubling time will be, instead of 25 years, will be 5 years. That is, for various reasons that are hard to understand or quantify, we can imagine a great increase in telescope aperture. Some comments I have regarding the growth of telescope aperture is, it seems to me the vision of individuals played a big role in the development of large telescopes. So if you imagine, think about Hale, the Hale 5-meter telescope. That was the vision of Emery Hale. The Keck, it seems to me, was the vision of Jerry Nelson. LBT was the vision of Roger Angel. These telescopes are extrapolations of the Keck and LBT. So the 20-meter, well, there's currently a proposal to build a 20-meter equivalent using 7 8-meter mirrors. So it's like an extrapolation of the LBT. The 30-meter and 42-meter are like extrapolations of the Keck. Another factor that could give rise to large telescope is technical progress. To go from the Keck to the 30-meter and to keep the cost below $1 billion requires a cost reduction of about a factor of 4 in the way that you build a telescope. So if you just extrapolate Keck to a 30-meter, it'll be more than $2 billion. But if you want it to be in a range of $500 million to $1 billion, then you have to reduce that cost by about a factor of 4. There has to be some technical advance to make that happen. There's also competition in politics. Well, you can imagine what ESO and TMT projects are currently watching each other very carefully, and they want to be first. So there's a lot of pressure to push as fast and as quickly as possible to build these telescopes. And then there's economics. I personally believe the rapid growth of telescope aperture, especially in this era here, it's not just these 3 telescopes, but there are about 16 8 and 10-meter telescopes built in this time period here. And that was far more than anyone ever expected when the first large telescope was built. And it's partly in my opinion, the robustness of the global economy. We've been very fortunate. For this kind of extrapolation to occur, I think the the global economy has to continue to be healthy. And we're in a very uncertain period, so the economics has a big factor in my opinion. Okay, this is some plots from this paper by Van Bell. He looked at the cost. Now this subject of what the cost of a large telescope is going to be is very controversial. But he has some data, and he believes, prior to 1980, you could guess that the cost would scale a diameter to the 2.8 power. Then new technology emerged regarding figuring of large telescope blanks. That dropped the cost and also changed the slope a little bit. So now he feels, the author feels, you could draw a line that's maybe d to the 2.5 power. And for the giant segmented telescopes, there's not enough time yet to do a decent plot. But I'll make but the plot, the curve shown here is d to the 2.5. And it seems to me it can't be, it's got to be between d to the first power, or let's say d to the second power, d to the 2.0, and d to the 2.5. And the reason is that a scaling law that is d to the 2.0 would be proportional to the area of the telescope. So it seems to me it would be hard to have a scaling law that's lower than d to the 2.0. But what's shown here is d to the 2.5. And what you can see is the cost of the telescope alone, if this is true, for a 30-meter telescope is about a little over $1 billion. Okay, now we have to correct for the very weak dollar now. So maybe 1 billion euros, let's say. A 42-meter would be way up here. Would be quite a bit more. Well, I should say make one more comment about these data points up here. See, this is the kind of large telescopes that are being planned in, say, roughly the year 2020. The 30-meter actually would like to be under construction in 2014. No, 2009 they would like to start construction. They will be finished around 2015 or 2016. But you can see how far off the curve they are. And if this curve is correct, you would expect the 30-meter to appear sometime near 2050. I'll be long retired, maybe no longer here, in fact. But this is very ambitious, and a 42-meter is even more ambitious. So it's very interesting to see how this all works out in the end. But as you know, building the telescope is only the first step, and the operations and instrumentation are quite important. And also the cost of instrumentation is going up dramatically. Some of the proposed instruments for Gemini are up to $70 million. I saw a number for the TMT instrumentation, and it's $250 million, including adaptive optics. These are huge numbers. So if you ask the question of what's the limit to telescope aperture, then I would say the question is, what is society willing to pay? Another point is that large collaborations, like in particle physics, can produce growth rate required for the extremely large telescopes. This point was made by Racine. He pointed out that the doubling time for accelerators was about 5 years. You think about CERN. CERN is the end point at the present time of the growth in accelerators. So Racine doesn't think that there's any reason why astronomy has to have a doubling time of 25 years. It could be 5 to 10 years if there are these large collaborations. ISO is one of them. Simon White has a very thoughtful paper on, which is the references here. He asked the question, but is it good for astronomy to be like the particle physicists and have everything, all your resources put into one large project? Another point I'd like to make is that as the telescopes become larger and larger, there might be a crossover point where it becomes more economical to go into space, where you don't have gravity and weather to worry about. This argument is made by Van Bell in this paper, and the basic reasoning behind this argument is that a lot more money is going into space development, or development of space telescopes, compared to ground-based telescopes. And so the slope for the cost curve is steeper. The relation between diameter and cost is dropping faster for space telescopes than it is for ground-based telescopes. And at some point, there's a crossover where it's more economical to build a telescope in space. And they think it's conceivable that between an aperture of 70 to 100 meters, it's maybe more economical, cheaper actually, to go into space and not worry about gravity and weather. Of course, this requires 3 or 4 generations of technology development. Okay? So we're very far away from that. And what is the future of small telescopes? Well, it seems to me in the U.S. and also at the IAC, we're quite fortunate in having a fairly large number of what you could say small to mid-sized telescopes. I didn't bother to spell out the acronyms. There's just too many of them. And you can add your own to the IAC. And there's also a fair number of sky surveys underway using small to mid-sized telescopes. And these telescopes will have a big impact on astronomy. So there are a number of questions of how to support operations. I personally think the rate of growth of funding is likely to slow down in the future. I mean, the kind of exponential growth we have seen in the last 50 years cannot continue forever. In the U.S., there's a trend toward private financing. DCT is a Discovery Channel telescope being built in Arizona. SDSS was privately funded. It's a Sloan Digital Sky Survey. The Allen Telescope Array is a radio telescope in California. TMT is looking for and public funding. It's conceivable to me that a single donor could be found to pay for this telescope, but not for the operations. There's also a trend toward partnerships. And in the U.S., we have these examples. WIN is the Wisconsin, Indiana, Yale, NOAO telescope. SOAR is the Southern Observatory Astrophysical Research. And this LBT is a huge, it has about 4 consortium members. And NOAO in the United States is looking for collaborations with universities. So there'll be and a final comment I have is how to keep the instrumentation group alive. I think the support at universities is critical. That's where there's a lot of young talent to be developed, and it's unknown how we keep going the way we're going and keep these groups alive at the universities. Okay, so those are my. This is the last slide, and those are my last comments. So thank you.
Questions, Humberto?
Alan, you mentioned very briefly survey telescopes. Survey telescopes can actually be an important factor here. I'm referring specifically to the LSST, which is it's a non-negligible budget that is coming out of the National Science Foundation astronomy budget. So that's also a significant drain on the available monies, and so they play a role. And so I was wondering what your comments would be on that.
Regard to the LSST specifically?
Well, in general, I mean, you mentioned survey telescopes only briefly, but I think they're an important factor.
Yeah. Well, I think right now it's in the U.S. at least there's quite a large interest in survey telescopes with NEOs. Pan-STARRS, for example, do more than just NEOs, but surveys in general, and go beyond what the SDSS has done. The SDSS itself is conducting redshift surveys to a larger sample. So the surveys will continue, and I do think they're very important. And I guess one comment in the light of what Simon West has been saying is that you don't want these large projects to choke off the smaller projects, and that's one of the underlying concerns for the future, because the operations can really eat up a lot of resources and leaving very little left for the smaller telescopes. It's sort of self-serving for me because I'm in charge of a 3-meter telescope, but I think there is a concern here.
More questions? Oh, I have a comment. I've been support astronomer of the William Herschel for years, and I tried to put some interest on remote observing there, but I failed. I hope your talk helps to do that, and I hope also we can collaborate. And you asked for IRTF time, then I asked for William Herschel CNG time. And I can observe in daytime, and you can observe in daytime also.
Yeah, that's a good point. But remote observing is not just for, I mean, the technique of using VNC for remote observing is also very, very useful for support, for the support astronomer to look at what's happening at the telescope without having to drive up to the summit.
You comment also that in queuing mode, for example, I have observations with a BLT, and when I found that were taken by someone, support astronomer, that I don't know, and when I analyzed this data, and I found something strange, I'm not sure if it is real or if it is due to the way they observed it, and it is very difficult to explore if they did it right. So
yeah.
I prefer to observe myself.
And my understanding is that you can do that at the VLT. I mean, you have that option. Yeah.
But you have to take a plane to Madrid, another 13-hour flight to Santiago, another 2-hour flight to Atacama, and blah, blah.
But if you're really dedicated, you'll do it.
Questions?